con compensadores dinámicos de potencia reactiva, más referido a lo que tiene que ver con STATCOM y STATCOM con almacenamiento de energía. Ese va a ser el tópico principal. Y lo vamos a relacionar, ¿cierto?, con lo que es los desafíos de hoy en día. Bueno, aquí un poquito de background de mi persona. Soy originalmente de Chile y ahora mi rol es de ingeniero de aplicación en Hitachi Energy Power Quality. Como experiencia, he sido antes ingeniero de proyecto, ingeniero de proyecto senior, y antes de eso, ¿cierto?, trabajé en lo que es Departamento de Desarrollo y Tecnología, en lo que era ABB, antes, ahora es Hitachi. Como experiencia de trabajo, tengo experiencia en diseño de SVC, diseño de STATCOM multinivel, técnicas de modulación y también diseño de condensadores síncronos. Es un poco para resumir, ¿cierto?, los años, la carrera de 10 años. Bueno, la agenda para esta oportunidad vamos a discutir lo que son los desafíos de los sistemas eléctricos de potencia de hoy en día, a lo que está ocurriendo a nivel global, para luego centrarnos en lo que son las soluciones de Power Quality de Hitachi Energy. Como ya dijimos, centrándonos en lo que es STATCOM y Enhanced STATCOM. Y ahí voy a explicar más en detalle a qué se refiere cada uno de estos dispositivos. Bueno, la idea es que tengamos una discusión abierta, ¿cierto? Entonces me pueden interrumpir en cualquier minuto ahí para ir teniendo esta discusión. Comenzando con los desafíos de la red de hoy en día. Bueno, uno de los grandes cambios que está ocurriendo a nivel global es la transición debido a la descarbonización. Está ocurriendo una transición de lo que es la energía fósil tradicional, ¿cierto? Las plantas que usan, las plantas de generación de energía fósil basadas en máquinas síncronas. Todo esto, ¿cierto? Hay una transición, va a ser reemplazado por lo que es la energía renovable, ¿cierto? Principalmente eólica y fotovoltaica. Bueno, uno de los desafíos que conlleva esta transición es el hecho de que las máquinas síncronas, los generadores síncronos, que son los que dan la fortaleza a la red y son los que dan la inercia eléctrica a la red. Y al estar siendo sacados del sistema y reemplazados por lo que es la energía renovable, esta inercia y esta fortaleza que está de cierto modo se está siendo afectada y se está está bajando lo que es esta fortaleza y esta inercia al sistema. Ahora, para definir lo que queremos, para definir lo que es la fortaleza de un sistema o la inercia, tenemos esta lámina donde la fortaleza se refiere a lo que es la habilidad del sistema, la capacidad del sistema para mantener estable su forma de onda de tensión. Esto quiere decir cuando ya sea en régimen permanente o cuando hay una perturbación en el sistema, lo que se quiere es que esta forma de onda se mantenga lo más estable posible, ¿cierto? Con la menor distorsión posible y que sea capaz del sistema mantener su estabilidad, de no entrar en un punto de inestabilidad y generar un colapso total del sistema. Entonces, otra forma de ver el nivel de fortaleza de un sistema es ver cuánto es la distancia eléctrica entre lo que es la generación, vale decir las máquinas síncronas del sistema, y la carga, ¿cierto? Si hay una impedancia muy grande entre lo que es la generación y la carga, también se puede ver esto como un sistema es más débil, al estar más alejado de la generación. Ahora, esto también se puede medir con lo que es el Short Circuit Ratio, que es un cociente entre la potencia instalada en un cierto punto de common coupling, PCC, dividido por la potencia que se está instalando, por ejemplo, en un parque eólico ¿cierto? Se está instalando ciertos megawatts, entonces se toma la potencia de cortocircuito de la red en ese punto donde se va a conectar el parque y dividido por la potencia nominal de ese parque. Eso nos da un cociente. Ese cociente nos da es un índice que nos puede indicar si el sistema puede ser fuerte o débil en ese punto, ¿cierto? Eh, Acá tengo una definición de SIGRE TV 671, el cual indica, por ejemplo, si ese cociente es mayor que 5, se puede ver como una red fuerte, que lo más probable es que no necesite un reforzamiento de incrementar esa fortaleza, pero si este cociente es menor que 3, se puede ver como una red más débil, en el cual lo más probable es que necesite un reforzamiento de incrementar sus niveles de cortocircuito o su fortaleza. En el caso de los condensadores síncronos, por ejemplo, o las máquinas síncronas, una forma de ver su contribución de nivel de cortocircuito en un cierto punto es con esta simple ecuación, donde tenemos que es el rating de una máquina, dividido por la reactancia transiente y la reactancia del transformador. Vale decir, todas las impedancias que hayan entre los terminales de la máquina y el punto de conexión, y eso nos da un aporte de corriente de cortocircuito. Esto es una forma también de ver la fortaleza que contribuye esa máquina específica o ese grupo de máquinas específicas. Eso con respecto a la fortaleza. Con respecto a la inercia eléctrica, lo que nos vamos a enfocar va a ser, voy a poner el puntero láser, ahí. Lo que nos va a enfocar va a ser va a ser la derivada o el cambio, la pendiente, ¿cierto? En el primer swing de frecuencia. Esto es lo que va a hacer la inercia, la respuesta inherente de las máquinas síncronas con su energía cinética almacenada en su masa rotante, ¿cierto? Va a ser esa respuesta, esa oposición, es la capacidad del sistema para oponerse a los cambios de frecuencia. Cuando hay un desbalance entre la generación y la demanda, ocurre un cambio en frecuencia. Entonces, la capacidad del sistema para oponerse a ese cambio en frecuencia es lo que es la inercia. Se resiste a ese cambio. Y eso viene dado aquí, en este primer swing, en esta primera derivada de la frecuencia, del primer swing de frecuencia. También conocido como rock-off, rate of change of frequency, el cambio de la frecuencia en el tiempo. Y como ya dijimos, es una respuesta inherente del sistema. Eso está antes de lo que es el control de la frecuencia primaria, el control de la frecuencia secundaria. Estamos hablando en el orden del segundo aproximadamente. Esto ocurre incluso antes del segundo. Es cuando esto ocurre, esta oposición al cambio de frecuencia. Ahora, si esta derivada, digamos, este cambio es muy rápido en el tiempo, puede llevar a valores de frecuencia, ya sea sobre frecuencia o bajo frecuencia, que puedan ser perjudiciales para tanto como para la carga como para la generación en el sistema. Y eso puede incluso hacer que los generadores se salgan de sincronismo y puede llevar también a un colapso total del sistema. Entonces, eso es lo que el rango, digamos, de definición de lo que llamamos inercia eléctrica. Ahora, estos dos parámetros, la fortaleza y la inercia, son grandes desafíos que se han generado a partir de esta transición de la decarbonización y de estar reemplazando la generación tradicional, la generación convencional basada en energía fósil, por renovables. A ver, ¿por qué? Porque lo que son los parques solares, parques eólicos, no siempre, o la mayoría de las veces, no van a contribuir o no van a aportar una corriente de cortocircuito cuando hay una falla. Estos parques renovables están conectados a través de electrónica de potencia, la cual en este minuto está desacoplada con lo que es la red. Entonces no aportan directamente con corriente de cortocircuito y no aportan con inercia. Se podría, sí, porque al final la electrónica de potencia es controlable, ¿cierto? Los convertidores que están ahí podrían implementar los controles para apoyar, ¿cierto? Para contribuir, pero en la mayoría de los casos no existe un apoyo. Entonces, el sistema está viendo dificultades, ¿cierto?, para mantener ambos, sus niveles de cortocircuito o fortaleza y los niveles de inercia. Ahora, basado en estos desafíos, tenemos acá el portafolio de Hitachi Energy, donde tenemos el control de la tensión, apoyo en lo que es la fortaleza, la inercia y también el control de la frecuencia, más relacionado con el control primario de la frecuencia. En lo que tenemos en la parte de control de tensión, tenemos lo que es el STATCOM y los HVDC, los condensadores síncronos y el Enhanced STATCOM, que ya voy a decir más en detalle de qué se trata el Enhanced STATCOM. Si ven, el Enhanced STATCOM están los 4 cuadrantes de los servicios que estamos presentando aquí. Para la parte de fortaleza, tenemos el condensador síncrono, el STATCOM con Grid Forming Control, porque tiene que ser capaz de aportar con corriente de cortocircuito. Y tenemos lo que es el híbrido, el condensador síncrono híbrido, que no es nada más que un condensador síncrono en paralelo con un STATCOM. Y de nuevo aquí tenemos el Enhanced STATCOM, que está presente en todos los cuadrantes. Para la parte de la inercia, tenemos el condensador síncrono con su masa rotante, que puede contribuir con inercia. El condensador síncrono híbrido, donde en realidad la máquina o el condensador síncrono es el que está aportando con la inercia. Y el Enhanced STATCOM. Y en la parte del control de frecuencia tenemos, bueno, los sistemas BES, los generadores síncronos, es algo más que se encarga de la frecuencia, del control de la frecuencia primaria, pero también vemos que el Enhanced STATCOM es parte puede también contribuir con este servicio. Ahora, para enfocarnos en lo que es STATCOM, el STATCOM de Hitachi Energy, la marca es SBC Lite, ese es el nombre para STATCOM de Hitachi. Está basado en tecnología de Voltage Source Converter, ¿cierto? El cual se refiere a que genera su propia tensión en los terminales del convertidor. Si genera una tensión, no necesita componentes, bancos de capacitores, bancos de reactores, sino que en realidad la inyección o absorción de potencia reactiva se refiere a adelantar la corriente con respecto a la tensión o atrasar la corriente con respecto a la tensión. Esa es la forma con esta controlabilidad de la corriente, se genera la potencia reactiva, inductiva o capacitiva. El Voltage Source Converter está basado en tecnología multimodular, multi-level, la cual se refiere a pequeños clusters de capacitores DC, los cuales se suman en serie y va construyendo esta forma de onda de la tensión en los terminales del convertidor. Al sumar un número de módulos o de células de pequeños pasos, digamos, como ven acá, la forma es bastante sinusoidal, y al ser bastante sinusoidal, esto se traduce en que el STATCOM genera muy bajitos armónicos. Estos armónicos resulta en que ya no se necesita tener grandes filtros de bajo orden para lo que son los STATCOM. Entonces, la solución completa termina siendo mucho más compacta, porque ya no necesita filtros para absorber, por ejemplo, en el caso del SBC, generaba armónicos bastante altos, los cuales tenían que ser filtrados. Por eso que el SBC tenía filtros armónicos y de bajo orden, entonces resultaban en una solución más con dimensiones más amplias. Pero en el caso del STATCOM, esto ya no es necesario y es solamente lo que es el transformador, reactores de fase y las válvulas. Y algo bien interesante que es el estado del arte de lo que es el sistema de control, que es el Grid Forming Control, que habilita el STATCOM ahora para también contribuir con potencia de cortocircuito, con corriente de cortocircuito cuando hay una falla. Mejora lo que es el fall right through, operar sobre una falla, y lo que es el balanceo de tensiones, ¿cierto? Inyectando corriente de secuencia negativa durante una falla, por ejemplo, una falla monofásica. El STATCOM balancea las tensiones de fase. Las válvulas del STATCOM para el portafolio de Hitachi van desde 3 megabar hasta lo que es 425 megabar con válvulas de high power. Y todo esto puede ser hecho en una sola rama. No se necesitan varios convertidores en paralelo para tener esta potencia, sino que una sola rama es suficiente, lo cual tiene muchos beneficios, por ejemplo, menos componentes, menos coordinación entre control, eh, menos componentes que pueden fallar, o sea, aumenta la disponibilidad, la confiabilidad. Y, y por otro lado, lo que es al tener una potencia más alta, va a resultar una tensión más alta y esto va a disminuir las armónicas, el nivel armónico eh, se va a ver disminuido porque el convertidor mismo va a tener un número mayor de células, el cual se va a traducir como pasos más pequeñitos de amplitud de armónico. Ahora, en cuanto a la redundancia, si estamos hablando de llevar todo a una sola rama, la redundancia se agrega al agregar más células en serie. Digamos, estas células que vemos acá, que son los clusters de C, pequeñitos que se van sumando en serie, esta redundancia se da agregando más de estas células en serie. Es como se obtiene la redundancia para el caso del STATCOM multinivel. Con respecto al grid forming control, ya dijimos que es un esquema de control, ¿cierto? Del estado del arte, el cual habilita el STATCOM para, bueno, más que nada, el STATCOM puede emula lo que es el comportamiento de una máquina síncrona. Están implementadas las ecuaciones de swing dentro de este sistema de control. Entonces el STATCOM es capaz de proveer esta corriente de cortocircuito al inicio del falla, o sea, reacciona prácticamente instantáneamente a lo que son los cambios de tensión del sistema. Y otro aspecto que es muy importante del Grid Forming Control que habilita el STATCOM para operar en redes con nivel de cortocircuito muy, muy bajo, vale decir, en niveles en redes bastante débiles. ¿Cierto? Donde este radio, este short circuit ratio que hablamos antes, el cociente, puede ser muy, muy bajo en cuanto con respecto al tamaño del STATCOM, puede, por ejemplo, ser la mitad, la red podría ser hasta la mitad, incluso más bajo que la mitad de la potencia del STATCOM y todavía el STATCOM es capaz de operar estable. Esto se debe al esquema de control en cómo se sincroniza con la red, ¿cierto? Eh, Tradicionalmente el esquema precedente se sincronizaba con la red a través de un PLL. Bueno, esto ha cambiado con el tiempo y con el esquema de grid forming control ahora la sincronización es distinta. Se usa lo que es un Power Synchronization Unit, la cual está basada en ecuaciones de swing y el sistema de sincronización es mucho más eficiente. El STATCOM es capaz de crear y mantener su propia sincronización, su propia, generar su propia ángulo con respecto a la red. Entonces eso hace que el STATCOM ahora pueda operar establemente, incluso si la red no es fuerte. Bueno, en realidad esto es es una forma gráfica de ver, el STATCOM es capaz de operar en redes desde muy fuerte hasta muy débil, incluso en redes aisladas. Eh, lo importante de esto es no enfocarse en cómo implementar, por ejemplo, el Grid Forming Control, porque hay una manera muy amplia de implementar de estrategias de control para obtener lo que es el Grid Forming Control, pero enfocarse más en lo que es la necesidad, en lo que es la prestación, el performance con respecto al sistema del STATCOM. Entonces, vale decir, cuando uno especifica lo que es el Grid Forming Control, hay que centrarse en eso, en la prestación, no en la forma de implementación del esquema de control. Eh, con respecto a la madurez de lo que es el Grid Forming Control, bueno, aquí se compara un poco lo que que es la tecnología precedente, que es el grid following, comparado con el grid forming. Lo que vemos, la tendencia hoy en día es en el mercado, lo que se está buscando más y más por todos los beneficios que trae este esquema de control es que el aumento, obviamente. Y acá en este gráfico de la izquierda vemos una comparación, las barritas negras son el grid following control, la tecnología precedente, y las barritas verdes son el grid forming control. Entonces vemos aquí cómo a partir del año 2023, este año, ¿cierto?, ha ido en aumento. Estas son las unidades que ya Hitachi Energy ya tenemos en servicio, Statcom en servicio. Acá en el gráfico de la derecha tenemos un zoom solamente de las barritas verdes, ¿cierto? Alrededor de 4 o 5 unidades tenemos ya este año en operación y esto va a un aumento. Si observamos acá una curva exponencial, que sería un caso optimista, de si continúa el mercado como está hasta ahora, para el 2030 aproximadamente, 2031, ya se tendrían alrededor de 100 unidades en servicio. Eso con respecto al Grid Forming Control. Y ahora voy a explicar lo que es el Enhanced Statcom. El Enhanced Statcom es el Statcom, tiene las mismas funcionalidades que un Statcom, pero se agrega lo que es almacenamiento de energía en forma de supercapacitores, lo cual habilita al Statcom para también proveer energía o potencia activa. Y la potencia activa tiene el mismo efecto de contrarrestar lo que es los cambios de frecuencia. O sea, aporta con inercia al sistema. Lo mismo que hace la masa rotante en un condensador síncrono o en un generador, ahora lo está haciendo el STATCOM a través de inyección o absorción de potencia activa. Este almacenamiento de energía se hace a través de supercapacitores, los cuales son más rápidos que lo que las baterías. Actúan en el orden por debajo del segundo, el cual habilita el STATCOM para que pueda tener un soporte muy rápido de carga y descarga de estos supercapacitores, haciendo que pueda cumplir con la funcionalidad de corregir el rock-off, el rate of change of frequency, el primer swing de frecuencia, y apoyando, ¿cierto?, a lo que es la estabilidad de inercia del sistema. Para la parte de la potencia reactiva se puede todavía tener 400 megabar en un sistema de una sola rama con cientos de megawatts en almacenamiento de energía por decenas de segundos, si se quiere. Pero obviamente eso va a impactar en lo que es el espacio y el número de supercapacitores y el dimensionamiento de la casa de las válvulas junto con la casa del almacenamiento de energía. Aquí vemos la topología del Enhanced Statcom. Es muy similar a tener dos ramas de Statcom conectadas en estrella, donde el neutro de cada rama está conectado al almacenamiento de energía, a los supercapacitores. El resto de los componentes es muy similar a Statcom, se interconectan estas dos ramas paralelo con un transformador, el cual se conecta en el lado de alta a la red. Y aquí tenemos un pequeño gráfico de lo que es la diferencia entre las baterías y el supercapacitor. Acá tenemos un artículo, el cual se ha escrito entre Hitachi, Siemens y Tenet. Se hizo en colaboración, en el cual se describe lo que es esta tecnología, el Enhanced Statcom, y cómo ayuda a la red. Y bueno, hay detalles aquí, les dejo el link para que lo puedan explorar. Aquí les dejo el link a otro artículo, es un trabajo grande que se está haciendo en Alemania, donde se unen todas lo que es la utility, 50 Hz, Amprion, Tenet, Transnet, para tratar de hacer una unificación o estandarizar los ratings del Enhanced StatCom. Entonces, acá hay un ejemplo de una tablita se menciona en este artículo, donde la potencia estándar es alrededor de 300 megabytes con ciertas prestaciones, ¿cierto? O requerimientos que se han puesto de acuerdo estas utilities, ¿cierto? Donde se ve la necesidad en cuanto a rock-off, en cuanto al almacenamiento de potencia y otros parámetros. Entonces aquí también les dejo los links para que puedan informar más de esto. Y ya para terminar, como conclusión, ¿cierto? Las redes están siendo cada vez menos convencionales, más centralizadas, se están integrando más renovables para lo que es la generación y hay una generación más distribuida. Las redes, si no se hace nada al respecto, van a tender a ser más débiles y una forma de mitigar esto es con tecnología de Power Quality para el control rápido de la tensión, la inercia y la fortaleza, digamos, o los niveles de cortocircuito. Y el Enhanced StatCom o Enhanced SVC Lite tiene la tecnología del arte, lo cual incluye la tecnología de Grid Forming Control, puede proveer potencia activa y reactiva para controlar tanto la tensión como la frecuencia. Y tiene también, bueno, el Grid Forming Control es una propiedad adaptativa que se adapta a todos los tipos de red, incluyendo todo lo que es nuestro sistema de control MAC, el cual también se usa en HVDC, ¿cierto? Que tiene una base instalada que es muy, muy amplia y una robustez bastante eh, reconocida a nivel global. Y eso es lo que tenía preparado hasta ahora. Espero que no me haya excedido mucho en el tiempo.
Muchas gracias,
¿Alguna?
Tomás. Yo creo que en
Sí.
función del tiempo, voy a formular rápidamente unas preguntas que se recibieron acá de las personas que nos están
Ujú.
participando. La primera, de cierta forma la has mencionado, pero bueno, comentarla acá. ¿El StatCon logra contribuir con el cortocircuito solo mediante lógicas de control o requiere algún hardware como complemento? Algo mencionaste, pero de pronto vale la pena ahí como resaltarle la respuesta.
Eh, no, en realidad la generación de StatCom que estamos diseñando ahora viene ya con el Grid Forming Control como base. Entonces, esta forma de implementar el control, como ya dijimos, viene con las ecuaciones de swing, que son las mismas de una máquina síncrona. Entonces, ya el StatCom de por sí es capaz de contribuir con corrientes de cortocircuito sin necesidad de un hardware extra ni nada extra. O sea, ya viene como parte inherente del StatCom el contribuir con potencia de cortocircuito o corriente de cortocircuito.
Ok, gracias. La siguiente es para un convertidor tipo grid forming durante una falla franca desbalanceada. ¿Cuál es la máxima magnitud de aporte de corriente versus su potencia nominal? ¿Y de qué forma se controla la magnitud de inyección de secuencia negativa?
Sí, esta es una pregunta, muy buena pregunta. La máxima capacidad del convertidor, y es una limitación física, es la mitad de su potencia nominal, porque la mitad puede ser usada para inyectar corriente de secuencia negativa, la mitad de su potencia, y la otra mitad necesita circular para mantener un balance dentro de lo que es el delta del convertidor. Entonces, respuesta rápida, digamos, es la mitad de su potencia nominal, puede ser usada para balancear el sistema.
Gracias. Otra que tenemos acá son como dos parecidas. Se tiene un comparativo, son dos en una, digamos, un comparativo de costo Enhanced StatCon versus StatCon más compensador síncrono. Y en esa misma medida hay una pregunta de cuál es el costo estimado para soluciones de StatCon condensador síncrono o soluciones híbridas en dólares por megabar.
Ya, esa pregunta, ahí no tengo una respuesta muy buena, porque depende mucho de lo que se necesite, de la necesidad. Depende mucho si la parte dominante son los megawatts o la parte dominante serían los megawatts. Depende mucho de qué otros servicios se necesiten. Si usted tiene, por ejemplo, una red donde se necesite mitigar armónicos, o tenga sobretensiones muy complicadas, o sea un fall right through bastante de alta duración, o si se necesita tener el almacenamiento de energía para mitigar lo que es el rock-off, un almacenamiento de energía muy grande, digamos, o por mucho tiempo. Entonces, todos estos factores van a influir bastante, porque si nos devolvemos acá un poquito en la diapositiva del Enhanced StatCom, el área de lo que es el almacenamiento de energía es muy amplio en comparado con la casa de las válvulas, por ejemplo. Entonces, si lo que se necesita es una corrección del rock-off por un segundo, no va a ser lo mismo que si tiene una corrección del rock-off por 10 segundos o 5 segundos. Entonces, eso va a variar mucho en lo que es el costo. El costo, porque es dominante la duración y las prestaciones para la cual se necesite.
Ujú, ok. El tiempo nos gana, hay muchas preguntas, pero
Ujú.
una última como para ver si
Sí.
de pronto logramos aprovechar. ¿Cuál es el estado actual de implementación del Enhanced StatCon? ¿Cuáles son los proyectos instalados o por instalar en el futuro?
Ya, tenemos varios, estamos participando en tenders en lo que es Estados Unidos, pero hasta ahora no tenemos nada en operación. En operación, una tecnología muy reciente. No
Ujú,
hay nada que esté probado, digamos, en operación hasta la fecha. Pero hay tenders que se están haciendo ahora creo que en Estados Unidos y en otros países, pero no estoy al tanto de qué
ok,
otro país.
ok, perfecto. Bueno, Tomás, muchas gracias. Muy
Sí,
interesante. Es un nuevo camino que se abre para los sistemas, teniendo en cuenta las restricciones que mencionaba al inicio de la nueva tecnología de generación. Eh, Muy agradecidos pues por este aporte y yo creo que estaremos viendo estos equipos muy de cerca y mucho más pues, en un futuro muy cercano.
sí. ¿Mm?
Le paso la palabra a Jorge o a Henry. ¿Tienen alguna inquietud o continuamos? Ustedes nos dirán.
Mu- Sí, muchas gracias, Mauricio. Muchas gracias, Tomás, por la gran presentación que nos acabas de realizar. Como lo dice Mauricio, muy pertinente para el caso, lo que estamos visualizando, especialmente cuando tenemos alta integración de energías renovables que no cuentan con buena o alta capacidad de aporte de cortocircuito, inercia, además de referencia. Estas soluciones son bienvenidas, el grid forming, la inercia virtual que se podía tener, es precisamente lo que está pues alrededor de lo que estamos buscando, persiguiendo para estas soluciones en la transición energética. Entonces, de nuevo, reiteramos el agradecimiento eh, por tu presentación y bueno, una feliz tarde, feliz día. Eh, a continuación, entonces, vamos a tener eh, la presentación de Chandana Caragüita. Chandana, bienvenido. Welcome, Chandana. Thank you very much for your contribution, for joining us. We are very happy to have you here as well. So my colleague, Manuela, will introduce your presentation, your biography, and afterwards you can start with the presentation. Thank you again. Ms. Manuela.
A continuación, damos la bienvenida al doctor Chandana Caragüita. Es ingeniero profesional con experiencia industrial y académica en sistemas eléctricos de potencia. Se unió a Transgrid Solutions en 2007 y ahora ocupa el cargo de vicepresidente de estudios. El doctor Caragüita es un experto en estudios de sistemas de potencia que incluyen HVAC, HVDC y FACS, y generación basada en inversores, solar, eólico y BESS. También participa en actividades de investigación académica como profesor adjunto en la Universidad de Manitoba. Bienvenido, doctor Chandana.
Thank you, Jorge and Manuela. So, can you hear me, Jorge?
Yes, we are hearing you. We are hearing you.
I assume that you can see my screen now.
Yes, we are seeing your screen. It's
Okay.
okay.
Yeah, it's already the presentation. Chandana, thank you very much.
Thank you. Yeah, today I'm going to talk about the technical challenges of HVDC and AC systems in parallel operation. Actually, before going into this, I think you all know that transgrid solutions involved with UPME on the feasibility studies of the Laguirre HVDC proposed for Colombian system. And so I will get some examples of that as well, like in my presentation. And again, like if you like have any question, we can discuss at the end. I will try to go in very slow, and please let me know like if you need more explanation or anything like that during the presentation. So yeah, about the AC/DC parallel operation, like you know that the situation similar to in Colombia, like there are many systems right now, like trying to get the renewable generation in remote systems into the load centers. So there is a significant growth in this application, and so the challenge is how to get this remote generation into the load centers. Like we need new transmission corridors, and we need new transmission mechanisms and so on. We can use either AC or DC. In some cases, AC in parallel with DC. So it all depends on the system requirements and the possibility of building new transmission systems. We know that it is very difficult to get the right of way approvals for new transmission lines anywhere in the world now. So because of that, there is a trend that we are using existing right of way when we build new transmission systems. So here we are talking about DC. So that means like we have to go with existing AC in parallel. So the other choice is to go for cables, but cables would be quite expensive compared to the overhead transmission. So that means like, so our objective here is to operate HVDC overhead lines in parallel with the AC transmission lines. And in some cases, it may be like on the same tower, like one side may be AC, the other side may be DC. And in some cases, like two different towers, but in the same right of way. So few examples, we got involved in both of these projects. One project is the Ultranet project in Germany. So this is a full bridge MMCVSC HVDC link being built right now. So by Siemens. And this is actually a unique application. So they decided to convert one of the circuits of a double circuit 380 kV transmission tower. You can see this double circuit transmission tower, like one side was converted to DC, the other side is AC. So that means like we have to operate 380 kV AC in parallel with 380 kV plus minus 380 kV DC. And Another challenge in that project was there were 110 kV transmission system underneath these big transmission towers. So that means like challenges are like the interactions between 380 kV AC DC and DC and the 110 kV AC. So all these challenges were there. Like we evaluated these challenges in detail. I will discuss a little bit about that bit later. And then the next one that we got involved was the Süd-Ost link in Germany. And again, like here, they are sharing the right of way. Actually, this is a 2000 megawatt plus minus 525 kV half bridge VSC bipole. And if you're familiar with this, the rigid bipole configuration, actually, this is a rigid bipole. That means there is no DMR or electrode, and it's like positive pole and negative pole and operate in the symmetrical mode all the time. So, and in this one also, like we have a certain part AC overhead line and the rest AC overhead line and the AC DC overhead line, and the rest is AC overhead line and the DC cable. So so we evaluated the interactions between the AC and DC for this project. So one of the main challenges with AC-DC parallel operation is the mutual coupling. We all know about this magnetic coupling, like between DC lines and the AC lines. And the one issue is the induced AC currents on the HVDC. Like we have high voltage AC transmission parallel to the DC transmission. So we see that on the DC lines, there are like 50 hertz or 60 hertz component appeared on the DC line. You can see these are the simulation results that we obtained for Ultranet project. And you can see the amount of distortion on the DC current, and this is significant. So we noticed that the current can come from both positive and negative poles, and then going to the ground as well. Like all these currents are significant, and we need some kind of some way to mitigate this. I will discuss about that a bit later. So what are the issues with this the AC current on the DC? So when we have a 60 hertz component on the DC side, this will modulate into a DC current and the second harmonic on the AC side. So that means the converter transformer will see some DC current and the second harmonic appearing at the converter side. So this will lead to main issue is the transformer saturation. So because of the DC current, so and the second harmonic, so that will add additional losses as well as like the contribute to the total harmonic distortion as well. Like so both of these issues should be resolved. So otherwise we will see the loss of lifespan of the transformer, and this will affect the, if we have filters with the HVDC, like this will affect the filter performance as well. So these are the challenges with induced AC currents on the DC, steady state induced currents. The second issue is the transient over voltages. So again, like transient over voltages can happen in both ways. So that means transient over voltages can happen when we have a AC fault. So the DC line will observe some transient over voltages. Similarly, when you have a DC fault, the AC line also can observe some transient over voltages. So because of the mutual coupling, and this is a major concern, and if you see that the transient over voltages are significantly high, like you need some kind of mitigation for this as well. And again, like our investigation showed that these transient over voltages highly depend on the AC system strength. When the system is weak or strong, like these, the transient interactions are quite different. Like, so these texts explain how it behave like under different conditions, but I'm not going into the detail. So remember that the AC system strength is also playing a role when we talk about transient over voltages happening because of the mutual coupling. When we have AC and DC on the same tower, the one major concern is AC to DC faults or DC to AC faults, whatever. Like, so basically intersystem faults. So we evaluated this issue for the alternate project actually. So what we saw that if these kind of faults happen, like there is a very large DC current flow into the AC system. So we need to detect this and reduce to zero. And this is usually done from the DC HVDC side. So similarly, there is a large AC voltage appearing on the DC. So you can see this, the huge AC component appearing on the DC lines. So, and we need to detect this and control this as quickly as possible. And then the last issue was the AC current flowing to the DC system. Now, like, somehow like we have to control the AC current. So we have to have a special detection mechanism, and then we need to trip both AC and DC as quickly as possible to avoid any damages to the system. And the last item that I want to talk about is the corona effect. So the concern when we have AC and DC on the same right of way is the corona effect. So the corona charges on the DC line are more significant than AC lines. So these may induce significant harmonics in the AC conductors. So these harmonics can saturate the power transformers and the CTs in the AC system and also increase losses. And again, like if we see, you can evaluate this at the planning level. If you see that the impact is significant, you need some kind of mitigation for the corona as well. So let's talk about some mitigation measures. So for the mutual coupling, so for the AC currents appearing on the HVDC, we need to somehow suppress these AC currents. The easiest way is to add the blocking filters. We can have fundamental frequency blocking filters added like this. Basically, we have to, usually we add the filters at the neutral, but close to the neutral bus because of the low voltages, and it's the cost is low. And usually, like we need 3 of them for each pole and the ground connection as well, if there is a ground connection, like and similar to the other end as well. And you can see the impact with and without filters. So if you design the filters properly, you can suppress the AC current significantly. And the other option is the full bridge HVDC converters. And this was the application in alternate actually. So with full bridge HVDC converters, the converter controls can do a much better job than half bridge converters, because with a full bridge HVDC converter, you can control AC and DC independently. So you can use this the capability to control the induced currents and as well as to detect the AC to DC faults and clear them using control pole detection logic. So we evaluated this for Ultranet and showed that this is feasible. So right now Siemens is implementing these controllers into Ultranet. And the other option is transposition. So what we observed that if we can transpose AC lines mainly, and in some cases DC circuits as well, and this is one of the most effective solution for most of these issues that we identified. So if you can transpose the AC line, we can easily get rid of the steady state fundamental frequency components on the DC lines, and the transient over voltages are significantly reduced, and you can reduce the corona effect as well. So, but the thing is, that transposition is not that easy. Like you need special towers to do this. But if you can do at least few transposition along the corridor in parallel, so that will help to reduce these the mutual coupling significantly. So here you can see some of the simulation results with and without transposition. And here, this is the DC current appearing on the converter transformer. You can see that we got rid of the DC current by having the transposition on the AC line. So the other possible solutions, like especially if you see a significant DC current going into the converter transformers, we can add the special controllers to suppress this transformer DC current. So basically, you have to add a parallel controller to the current control of the HVDC system, and that can suppress the DC current. And then another requirement is like especially the AC to DC faults and the transient over voltages, we need fast fault detection logics and clearing mechanism. So to reduce the impact of the other system. So so these are the solutions that we commonly use for to mitigate the mutual coupling. So I discussed about the issues and the solutions, but I'm going to discuss few more things related to the AC/DC parallel operation, especially when we have the two systems connected to remote renewable generation, similar to the UPME application. In Colombia application, you know that these collector systems are to basically the renewable generation. So these are connected through the long AC and DC lines. So that means this is a very weak system. So we have a very weak system in the rectifier. And we need special mechanism to handle such systems. Like one issue is the requirement of the grid forming HVDC converters. The rectifier here should be in grid forming mode. So usually for offshore application, when we have single HVDC connected to offshore wind farms, we don't have to do grid forming. We can use islanded mode of operation. This means the voltage and frequency are kept constant. So the frequency is always maintained at 50 or 60 hertz, and the terminal voltage is controlled by the HVDC converter. This is the common mode of operation in most of the available offshore systems right now. But when we have a parallel AC connection, we cannot do that. So we need the properly designed grid forming converters. So in our study to UPME about the HVDC link, the report is available online. So you can see that we showed that the grid forming HVDC converter can maintain the stability of the system. And in addition to that, like we can have special control logics to control the power transmission in the parallel AC lines as well. All these things are discussed in the report. So that is one of the requirement for such a system. Another requirement is, like, let's say we have a fault in the inverter side. When we have a fault in the inverter side, it's kind of a load rejection for these wind farms or solar farms. So that means like we need some kind of way to absorb the energy during the faults at the inverter side. So right now for the offshore systems connected to the through the HVDC links, we use DC choppers for this purpose. So you can add a DC chopper to the HVDC during the fault on the inverter side. So you operate the DC chopper and absorb this energy coming from the offshore system, and so the system stability is preserved. So this is the common way of doing this for offshore system. But in recent projects, especially the renewable generation, onshore renewable generation, similar to the Colombia system. So we propose AC choppers. So instead of this DC chopper, we connect a chopper on the AC side, and this is a much cheaper solution because when you have a DC chopper, it's like a HVDC converter valve. Like we need MMC. Usually we use MMC converter for the DC chopper, but when we have an AC chopper, we can use thyristor-based AC choppers, and the solution would be much cheaper compared to the DC chopper. So, and these are some of the results that we obtained for a fault on the onshore system. So we can operate the AC chopper to keep the system stability during this disturbance. But there is an added advantage of the AC chopper. So for the DC faults, if you have a DC faults, if you have a DC chopper here, nothing to do with the DC chopper, we have to trip the DC chopper as well. But if we have an AC chopper during the DC fault, we can absorb this excess energy using the AC chopper and keep the stability. That is one way. So that means, like, let's say we have a permanent DC fault here, like we absorb the energy and during the transient, and then order for the wind farms, some of the wind farms to trip in order to keep the power balance. But tripping is not the only solution available. You can actually ramp down the power and operate the AC chopper such a way that you keep the power balance while the wind farms are ramping down the power. You can see here the wind farms are ramping down the power to the level that we want, and the chopper keep absorbing the excess energy of the system. You can coordinate these systems together. So that means we don't have to trip the wind farms. The wind farms are still operated. So, but at lower power level, as soon as the HVDC comes back, we can ramp up the wind farms and transfer the power. When we have parallel AC connection, it's even easier. Like we can decide like whatever the power that we can transfer through the AC line, the rest we can ramp down using this logic. So this is the application of the AC chopper. Actually, we recently proposed a CGRE working group for to evaluate the performance of AC and DC choppers, and it's actually B400. So and we are looking for the members. Like if you want to contribute into this, like talk to your regular member in your country, B4 regular member, and join the working group with us to evaluate these feasibilities further. So with that, I'm going to summarize my presentation. So basically, yeah, there are technical challenges with when we have parallel AC/DC systems, but a properly designed system can meet all these challenges, and you can design the system, but you need to design it from the beginning. And then the second item is like for a HVDC application like in Colombia, we need grid forming HVDC converters at the rectifier. So so you have to design these converters such a way that you can keep the power balance between AC and DC systems. So, and the last point is for a application like in Colombia, the AC chopper would be a feasible solution to absorb the excess energy during the disturbances. This need to be further evaluated if you are going on this direction. So with that, I will conclude my presentation. We can answer some of the questions that you have.
Thank you very much, Chandana, for your great presentation. Without a doubt, it will be very useful for our intentions for Colombian project that you know with special high detail. Thank you very much. We will use these conclusions to supply our intentions and or what we are looking for these solutions. Yes, we have some questions. The first one is from Jorge Mola. How do you study the AC to DC faults in a simulation software? How do you introduce, is the same question, how do you introduce the AC component into the DC line?
Yeah, the simple answer is like you need to model both of the systems. Like you can model a reduced system, reduced model of your AC system, and then you have to have a detailed HVDC model. This should be done in EMT softwares like PSCAD. So, and then you need to include the frequency dependent characteristics of the both AC and DC lines. Basically, create the reduced system with the HVDC embedded and do the simulation in EMT and evaluate the coupling. So this should be done in EMT, and I showed some of the results during the presentation. It's all were done in EMT softwares. Yeah.
Okay. The next question: in what type of scenarios that situation, AC to DC fault, is prone to happen? Are there any scenarios that are of interest for such a fault?
Yeah, but the thing is, yeah, you have to look at your like corridor, like how you have the two system. If the two systems are going in parallel continuously, there is the possibility of having AC to DC fault would be very less, because it would be the collapse of a tower or something. So then it is not applicable. But like if you have crossing points and where these AC and DC crossing together, or if you have low voltage AC underneath DC, so then the possibility of having AC to DC faults would be high. So you have to evaluate your application and find out whether this is a feasible issue. And if it is feasible, you have to find out the impact of that. Yes.
Thank you. We have the next question from Jorge Mauricio Reiza. According to the state of the art in AC and DC shared transmission, for the future low inertia Colombia network, how feasible will it be to have high power AC DC shared links? Would HVDC LCC links be feasible considering the characteristics of this technology?
We won't go for LCC at this point actually, because now the thing is VSC is matured. Like even when we talk about we did the study like almost like 1 or 2 years ago for UPME about the application in Colombia. We even at that time we proposed VSC. Now we are confident that if we want to even achieve 3,000 megawatt, most of these major manufacturers are offering 3,000 megawatt VSC. So even at 500 kV DC voltage, like actually we propose 600 kV DC. Definitely, this is feasible, and we don't have to go for LCC. And now the thing is, what we know from the manufacturers, they are reluctant to offer LCC because they are mainly focusing on VSC. And and the other thing, since this system is connected to a weak system and we need to operate in grid forming mode, and with LCC, it would be quite challenging to go for grid forming with a weak system, and we may need a lot of synchronous condensers and so on. So, but the VSC would be a better solution for sure. And considering today's market, I would definitely say that grid forming VSC would be the solution.
Okay, thank you. I have a question. Do you have any comment related to insulation coordination when we use the same tower for AC and DC? Let's say an existing AC tower to hold an HVDC circuit.
Well, yeah, that's a really good question, Jorge. Actually, I should have talked about insulation coordination as well. Like, yeah, it would be quite challenging, especially the lightning would be very similar because we have to anyway consider if it is overhead system, we have to consider lightning strike on both AC and DC. So, but and again, like we may have to consider backflash over issues and so on. So like there are added challenges with insulation coordination when you have AC and DC on the same corridor. And another concern I quickly mentioned about that transient over voltages because of the faults on the other system. So this will affect the insulation coordination as well, especially switching studies. When you do the switching studies, you have to consider the faults in both of the systems and design for the two systems together. It's very important. So even like, let's say, if you are going to have both AC and DC on the same tower, so it would be quite challenging, and you may have to change the arresters connected to the AC system as well. So these things should be carefully evaluated at the design stage. Yes.
Okay, Chandana, very clear. Okay, again, thank you very much for your great contribution. And we will use these conclusions for our work, and we hope that in the next future we can work together with these intentions. Very much welcome, Chandana.
Yeah, thank you very much, Jorge. Thank you very much, everyone, for inviting me for this great event. Actually, I see that more than 150 people here. So
yeah,
I hope that everyone enjoyed my presentation, and definitely. So I invite you to join through CGRE as well, like to collaborate with each other. And yeah, about the working group, Jorge, I mentioned about that. Like, so we have this new working group on the dynamic, active and reactive power supporting devices for VSC systems. So we are going to, I saw the previous presentation as well, the STATCOM with storage, like, so grid forming STATCOMs. So in this working group, actually, we will talk about AC/DC choppers and usage of synchronous condensers together with VSC systems and the STATCOMs, either for reactive power support or the grid forming purposes. So we will evaluate these feasibilities in the working group. It is B400, B4.100. So I invite you to join the working group through your the country's B4 representative. Yeah, please contact your country's B4 representative.
Okay,
yeah, thank you very much. Yeah.
Excellent. Yeah, we will go after that shortly. Thank you very much for your advice and contributions, and we hope to meet in the next future.
Thank you.
Best regard to friends at TGS, please.
Gracias.
Gracias.
Agradecemos al Dr. Chandana Caragüita por su valiosa presentación. A continuación, damos la bienvenida al ingeniero Benedikt Renigner. Es ingeniero electricista de la Universidad de Aachen de Alemania. Posee certificación PMC y sub-PM-CIP de Siemens. Recibió distinción Talentos HVDC. Ha participado en la puesta en operación de proyectos HVDC como Misurata East, Cometa e INEOS. Es ingeniero líder en HVDC de Siemens Energy para los proyectos GridLink, Celtic y NEOM, entre otros. Es instructor y mentor en sistemas HVDC, así como coach para nuevos sub-PMS CIP. Bienvenido, ingeniero Benedikt.
Hello, muchas gracias, Manuela. Yeah, I will share my screen as well. One second. Yeah, I have to admit, I know since yesterday that I have the chance to give this presentation. So yeah, I'm not really super prepared, but I hope I can anyway give you some useful information for today's session. So yeah, let's start right away. First, a little bit where we are. Again, working for the Grid Solutions department in Siemens Energy. One important task is, of course, the energy transition worldwide that we are playing. We are about 3,000 employees in our different areas. It's not only HVDC, of course. We have also the FACTS, the substations, where we are working and give really a full picture then to our customers that they can participate in this energy transition, which is ongoing currently. The most important thing, if we are getting asked to provide a solution, it's not only the requirements from the customer, it's the way we have to achieve this solution. And we have 3 different columns here, which we need to bring together. And this is, the solution must be affordable. Of course, the solution must be reliable. This is why customers approaching Siemens Energy. And the solution must be sustainable, of course. So we cannot build like it was 20, 30 years ago, where everybody was just building to make it possible. Nowadays, it's very important for us to make it more sustainable, reduce the CO2 footprint, maybe even do certifications of the plant for CO2, looking for new materials, reduce concrete, all this stuff. It's important to develop a solution which is state of the art. It's not only the HVDC or the pure transmission of power, it's everything what comes besides that as well. Then at the moment, looking on the global market, what we are providing are solutions in HVDC Plus, which is our brand name for the VSC solution. We really don't see a big market for the LCC solution. In our area, it's called Classic HVDC, the Cyrostar HVDC. So we are really focusing on the VSC solution because the majority of the market is now asking for the VSC solutions. Again, in the older days, it was really power transmission from A to B. We heard it earlier today when my colleague explained the Bellomonte HVDC. This is a very good example for LCC, really transmitting a huge amount of power from A to B. but it's getting more and more. It's not only the power transfer, it's also the nice additional features we have in the VSC HVDCs. We saw it also from Hitachi Energy, the STATCOM solutions. Also, this is possible to a certain extent with the HVDC, with the VSC especially. That's why this is used. What we can see here, what is one of the big features, let me also switch to my pointer. Yeah, we can really use the active power and the reactive power. It's not only that we use active power and yeah, reactive power is coming some kind of a side effect and we cannot control it. Here, we really can control both independently, and this gives us a lot of opportunities for for stabilizing the grid further, and not only for power transfer. What we add here and also is, for example, black start to really power up a grid, or to make it possible to use the HVDC in an offshore wind farm to transmit power from offshore wind to the shore. Even vice versa, we did that already, that we transmit power from shore to an offshore not wind farm, to an offshore oil facility. And yeah, also the footprint what we're using in the HVDC in VSC is much smaller than in Classic. I have another picture a little bit later, because typically we don't need any filters for low frequency AC filters, so the footprint can get very small. And this is especially in crowded areas in Europe, for example. It's always difficult to build new infrastructure. And the smaller we can build an infrastructure, so the more likely is that we can really get this solution approved, and we can start building the solution. Okay, well, yeah, what makes our HVDC? Where's my? Why it's not continuing? Sorry. Yeah. How do we build our HVDC? So the real core of the VSC is the IGBT. And what we are using here is not really a super special, super sophisticated HVDC IGBT. It's a standard IGBT. And this makes it really good, because then this core element is broadly available. And also HVDC is growing fast and it's big, but looking on the market, it's still a small area. So whatever device you're using, which is solely developed for HVDC, it makes it a bit complicated. If we go for mainstream equipment, that means there's a lot of R&D behind, there's a lot of service available, there is a huge production capacity behind. So if there's maybe even in a factory a problem, there are other factories who can produce the IGBTs. Same IGBTs, for example, here are used in traction control or big drive control, and this is perfect for us. We are looking that we really, the HVDC itself, it is a quite unique solution, but we are trying to put broadly available subsystems together to this unique solution. The same we are going to do now with our new control system, the Grid Flow Plus, where we are using control hardware, which is broad available and which has more functions than only HVDC. Let me see if I said everything. Yeah, I think so. Yeah, and taking these broad available product, we are putting together then our very special product, our power module, what we are using then to build our half-bridge converters. At the moment, we are using mainly two types of half-bridge modules for our MMC converters. The first one is this 4.5 kV power module, what you can see here. And yeah, the IGBTs are inside the case here. The outside here, you can see there's a thyristor for protection. There is another bypass switch also for protection. And this is a very proven module. We have thousands of it in operation. That means also we have a very broad experience now with it. And as of today, we can build solutions up to 3 kiloamps DC current, so meaning we can build a 3 gigawatt VSC converter with that type of module. And the second module, what we are having in operation or in execution, is our 6.5 kV module. That means the blocking voltage is higher in that module. The consequence is, for example, for 500 kV solution, we need less modules. And yeah, this can be interesting if losses is a very big topic, or also if we need to build more compact, if we have to reduce some space here and there, then this solution is a good choice. What type of module we are using? It's always for every project a new decision. And yeah, we are trying to get always the best solution for the specific project. It's not really that one module is better than the other one. We always need to look at the whole picture, and then we can take a decision what makes more sense also for the customer. And here we have possibilities for currents up to 2.4 kiloamps. So this module we are using, for example, now in the German project, which was also shown before, Südlink, Südostlink, which is a 2 gigawatt bipole project. Yeah, and putting everything together, then we are ending up here with the converter towers like this. And yeah, the key aspects again of our MMC converter is the current rating. As said, we can go up to 3 kiloamps. And the voltage level typical at the moment is up to 525 kV plus and minus. So meaning the real DC operating voltage is 1050 kilovolt. We can also go to 600 kV, always a bit depends on the factors, what we are having here, what we need to serve. Our converters have very low losses, which is very important because, yeah, no customer get paid for the losses. So we strive here to optimize that. We have a very good fault rate through capability. Black Start we mentioned already. We can build it in a very compact layout. And we have a high availability reliability, which makes it possible that scheduled maintenance can be done only every 3 years. So before it was maybe every year, where you need to shut down the system to do some repair works and maintenance works. And now we can increase that really to 3 years interval just by using some more modules per phase arm. Meaning if 1 or 2 or maybe even 5 modules would fail over the years, we don't need to shut down the converter. The module is getting bypassed and we can just continue the operation until the next scheduled outage. Yeah, how does the converter station look like? This is something we want to see in the next pictures. Sorry. I have here as an example a symmetrical monopole. Some years ago, the symmetrical monopole was the one and only solution for VSC. Also, our systems in operation, in commercial operation, are all monopoles. And still in the future, it will remain important, the monopole. But now there was really a strong shift towards bipoles, but the stations are quite similar. So the conventional part is, of course, the AC switchyard. Here in this example, it's an outdoor switchyard with AIS equipment. Sometimes also GIS equipment is required. Depends again a little bit how much space do we have available. Are there any constraints from the authorities maybe that they don't want to have this really as a visible infrastructure project? So we could do it also indoor with the GIS. Here you can see also some little filters. Here, this is not really always necessary because the big feature of the VSC is that it's not producing really any harmonics, but maybe it's amplifying harmonics which are already there in the grid, and then we need to filter that out. Or also, if you're looking more in the high frequency range, there might be PLC radio interference that we need to consider limits. And then also we need some high frequency filters to not disturb the existing infrastructure close by. Number 2, very normal stuff, spare part building that the customer is in the position to repair if necessary, and also that we can fulfill our guarantee figures for availability. We need spare parts available. Number 3, the heart and soul, of course, the converter hall. In this case, we have also the DC halls, 2 here and here as indoor solution. This could be also outdoor. Again, depends really strong on the project, on the environment that we have there, on the limits which are given for EMC. And then we can decide if it's indoor or outdoor. Interface transformers as coupling to the grid, limiting of fault currents, and also adapting then the AC voltage which is needed for producing the DC voltage. Number 5, here our normal infrastructure, which also is important for an HVDC station. We are talking about infrastructure. In a lot of cases, this is critical infrastructure, so it needs special protection against intruders with a special fence, maybe double fencing systems. And also, yeah, we need streets, we need normal facilities that the people can work there in a very safe manner. And number 6, as we are talking here about IGBTs, they produce heat, and we need to make sure that the IGBTs and the whole power modules are sufficiently cooled always. That's why we have here our outdoor cooler banks as an important part. Diesel generator. Normally, our station is self-supplied via the interface transformer. We use the tertiary winding to supply our station for auxiliaries, but for example, for startup or especially during the black start, where also a local DSO grid is not available, then we need to use diesel generators to support the startup of the system until the station is operational and we can support ourselves again from the tertiary winding. And of course, it's not all about HV equipment. Also, we need to have a place for all the control systems, for the operators to be housed, also to have normal facilities that you need, bathrooms, everything what's needed that our people, that the customers' people can work there in a very good manner on the station. Even though most stations are unmanned nowadays, also for scheduled maintenance, it should be possible then to have a good working environment. We introduced as some kind of clustering names. We have here as an example the VSC 900. That is then a symmetrical monopole up to 1000 megawatt, typically at plus minus 320 kV. When a customer is approaching us with an idea for an HVDC, with this, yeah, we have some of these brand elements, then we can very fast generate a layout, generate a single line, and providing a possible solution for the customer. Also then really in supporting in finding the best solution for the situation, because there are always more than one solution possible. And of course, we're also supporting here in finding a good solution. Yeah, I said this is the symmetrical monopole solution. And the biggest what we would have is the VSC 3000. This is then a VSC solution in the bipolar configuration and up to 3000 megawatt. So meaning 2 times 1500 megawatt at a voltage of plus minus 525 kV DC, or also possible 600 kV DC plus minus. Here in the example, a lot of stuff is outdoors. This we can do if it's possible with the authorities, if the environmental conditions allow for it, then of course it's the most cost optimized solution. We can see the DC yard here is outdoor, and only really the converter is indoor, which is the bare minimum, which need to be indoor, obviously. AC yard is outdoor, transformers are also here outdoor. And we have a very big control building as a single floor building. Also, that is always the cheapest solution. Yeah, but this layout is only possible if we have not really space constraints or permitting constraints. Comparing that to the old LCC world, the pictures are not scaled in the same scaling. You can see here the LCC plant for 2 times 1500 megawatt bipole would require approximately 470 by 400 meters, mainly due to all the AC filter banks what you need. And the same transmission capacity we can achieve with the VSC solution in only 230 by 200 meters. So it's really like, basically it's half of it. And this makes it then interesting, especially for, yeah, if you build it close to a big city where finding a good plot is always a challenge for our customers. So here it's very compact, and you have a very high transmission capacity. Do we want to go higher than that? I mean, from LCC, we know that also 8 gigawatt bipoles are possible. At the moment, we see the 3 gigawatts as a quite good limit, because when we design the system, we don't design it for straight ahead power transfer. We need to design it for N-1 conditions. And a trip more than 1,500 megawatt is for most of the customers very challenging, or even it's not possible due to the grid codes. So also in Germany, there's a very strong, very meshed grid. We are building only 2,000 megawatt bipoles, even though it could be bigger theoretically. But due to the contingencies we need to fulfill, the 1,000 megawatt in that case is a good, it's a good limit. And other customers allow up to 1,500 megawatts. So we see here really that this is a very good value to provide to the majority of the clients and to really provide the majority of the projects on the market with. Also important, of course, is the performance, what we have. And I just giving a little example here. For AC and DC fault rates through for our half-bridge converter. On the AC side, the converter is also during AC events is capable of injecting really reactive current as needed to support the AC fault and to make sure that the grid remains very stable as far as possible. And for DC fault rates through, DC faults we need to clear with the AC breaker. In the majority of the projects, it's anyway with the cable what we see. And if there's a failure on the DC cable, we anyway need to open the breakers, and there is not possible to re-energize again. Nevertheless, could be also with overhead line content. Then we have fault clearance times of the area of 1 second, roughly. And if the event is on one pole, the other pole can still operate, especially in the bipole configuration. So there are a lot of possibilities. Also here, dynamic performance, it's very important really to talk with the customer to get really the boundary conditions from the customer and then decide in which way we can optimize the control and protection system to make it as adapted as possible for this situation. Also, one part I wanted to share is what we can do with the VSC is we can do it offshore. Here, the VSC 900 single mode monopole solution for an offshore wind farm. You can see here that everything what we saw before on the picture is now packed inside this platform. Here, of course, it's very important that we build it as compact as possible. Air insulated switchgear is obviously no option for an offshore platform, so everything is GIS. And also here we are using now more and more in Siemens Energy, we call it blue HVDC. So this is an HVDC which works with clean air, not with SF6. We have the converters here, also indoor, and the DC reactors, the transformers. We have 2 times 100% transformers because here it's not very easy to change a transformer. That's why we have this included. The good thing for cooling offshore is that we have plenty of cooling liquid available. Namely, it's the seawater. So we can use the seawater to cool the transformers, to cool the converters. Of course, with more than one circuit, so we're not pushing seawater through our converters. But with heat exchangers, then we can take out the heat, realizing this very compact solutions for offshore wind connections. And then, where did we actually built all this stuff already. So you can see it on the picture here. Green are the LCC solutions, also the Bellomonte solution here. The white ones are AC grid connection, and the green, the blue ones are our VSC solution. And you can see here a very strong focus on the European market. It's not 100% up to date, this slide. We have also now some in the US. Here in India, we can see one. Yeah, there are a lot of other markets are emerging, and also the South American market. We would be happy to share our experience here and to build up the first VSC solutions in South America, in Colombia. There are also, I think, opportunities upcoming where our VSC solution could help to fulfill the requirements for such a project. And just, I want to close with two examples what we have. Both are in operation for a bit longer time. Still, we are very proud of it. One is the Allegro interconnector between Belgium and Germany. This is really the classical 1000 megawatt solution, which we have installed plenty of times, onshore, offshore here. And the other one as an offshore solution is the Borin 3 platform in the North Sea. This is, yeah, the pictures are very unique. This big yellow boxes here in the middle of the sea. This was also almost 1 gigawatt. I think it's 900 megawatt solution in the open sea. And we are using here also plus minus 300 kV solutions. All right, thank you for that. I saw in the chat in between, there are some questions popping up. Let me just see if I can see where it was started. I think here from Jorge, for the future now, low inertia Colombia network. Yeah, low inertia network is a thing. For LCC, you need basically on both sides very strong networks. Whereas for VSC, you can do it with, at least on one side, you need basically no grid, like we do it for offshore. We are generating the grid from scratch. But then the second station need to be somehow in a stable grid, because the energy need to come from somewhere. We can do a lot. And now also with the grid forming controls, we have a lot of possibilities to work also on two sides with weak grids. So if you are having a weak grid, then the VSC solution is definitely a much better choice than looking for LCC, and you can operate really on a wide range here. Then Henry wrote another question.
Benedict. Yeah, thank you very much for your great presentation and contribution for our project here in Colombia and our expectations. I can see that you started to read the questions in the chat. Thank you very much for this. Yes, if you want me, I can read the questions.
Sure, go ahead.
Okay, thank you very much. From Henry Smith, how is the relation of the costs of VSC solution using it in lower powers like 300 megawatts or 400 megawatts or 500 megawatts, comparing with classical 1000 or 1500 megawatts?
It depends a little bit. We're having these discussions just now with some clients. They have a very low power, but they want a lot of functionalities. They want it in the bipole configuration. So then if you look for the price per megawatt, let's say, the lower you go, the more expensive it is, because there is a lot of things which are fixed, like the control system, it's fixed. The size of the converter is related to the DC voltage. So if you say, I want definitely 500 kV because I want very low losses on the line, but only want to transmit 300 megawatt, then the converter is heavily oversized for the voltage. which meaning you need to pay for a big converter, and only the transformer then is something that you can play with, where you can save a little bit. But yeah, it's the case. If you have very low power, you should go with the symmetrical monopole to have it more cost optimized. And then if it's 300, 400 or 500, the price difference is really low. And if you say, okay, because of availability, I want a bipole solution, then there's a little jump because you have the double number of transformers, for example. It really you need to look on all the figures here, but low power, as said, per megawatt is a bit more expensive than higher power solutions. Yeah.
Okay, thank you very much. The next question from Jorge Mauricio Araiza. Taking into account the current advances in HVDC transmission and what is being developed, assuming that it should be planned for a useful life of a length of 30 years, in addition to the massive entry of renewable generation. And we have two embedded questions here. The first is, that was the introduction. The first is, can we conclude that the most advisable as a long-term solution would be VSC instead of LCC? If you want, you can answer this first, and I go with the next one.
Yeah.
Afterwards.
Okay. Yeah. The lifetime of 30 years, 40 years, what we can do, only looking on that, and it could be both. So if you say, okay, I have really big hydro plants in the north of my country and big cities in the south, you can go with LCC. But as he said there already, the renewable generation is increasing. That means that the inertia of the grid is decreasing. And then it makes much more sense to go on VSC, because here we are more flexible with the weak grids, and we can add also additional stability functions. For example, we could also do it then in a multi-terminal, that later you say, okay, in between the two stations, I want to build a third station because there is an opportunity for huge wind farms, solar, whatsoever, or we need there a little bit of energy and make a hub there. Then you have much more flexibility with VSC solutions.
Okay, thank you. And the next one, inside the same context, is up to what power level can we recommend? Can the recommendation be maintained?
Yeah, what I said before, at the moment we are having solutions for a bipole with 2 times 1,500 megawatts available. We have also symmetrical monopoles in this range in our portfolio. So this is really then depending a bit on the grid where we are connecting, what makes sense. Sometimes it would make sense maybe to have, instead of one big monopole, building a bipole with 2 times 700 megawatt, for example, to have a better availability, reliability. So this depends really strongly on the grid where we are connecting, or the 2 grids which we are connecting here.
Okay, the third one, the last embedded here, is are the investment and operation costs of VSC competitive with LCC?
Yeah, if you would have asked the questions, I don't know, 10 years ago, then everybody would say, no, VSC is much more expensive and you have higher losses and everything is more expensive, but you get a little plus in functionality. But nowadays, we as Siemens Energy and our big competitors do the same. They invested heavily in the VSC technology, meaning we are decreasing losses, we are increasing availability, reliability, and due to the high amount of projects which are served, meaning that the average price per megawatt in VSC was dropping a lot over the last decade. So point number 3, really, cost is not an option or not an argument anymore if you say I want to go for VSC or LCC, because LCC is so much cheaper to build and operate. This is not the case anymore.
Okay, and the next question from Henry Smith. Can you tell about some experiences with VSC for low power, let's say 100, 200 megawatts?
This we could also offer. We call that not HVDC, we call that MVDC then, so medium voltage direct current. There we have in our portfolio some containerized solution that really a lot of parts are built up in the factory, are pre-tested and then shipped in modules to the site, which also is decreasing then the installation time on site a lot. And we could have these schemes much quicker in operation compared to the big converters where we build everything step by step on the construction site.
Okay, thank you very much, Benedict, for your contribution. Yes, without a doubt, now we have smaller footprints for BSC projects. The IGBTs have grown up. Now you said 3 kiloamps. The powers have decreased, so it is a very great solution, very interesting solution, and also the control possibilities. So BSC projects are very, very, very interesting. So thank you again, Benedict, for this presentation, for being with us. We hope to meet in the future again in this event, and we hope you a very good day. Okay, so
thank you for the opportunity, Jorge. Thank you
very much, Benedict, again. Okay, creo que hemos llegado pues al final de este evento. Agradecerles pues por la asistencia a todos quienes estuvieron pues todo el tiempo, lograron pues por las obligaciones que se tiene y más que es un evento tan extenso es difícil sostenerse. Quedan las memorias, las grabaciones y de nuevo pues la invitación a que formen parte de SIGRE del B4. Estaremos pues gustosos en recibir algunas de sus digamos propuestas para conformar sus grupos de trabajo. Ustedes organizan, digamos, la idea. Luego esta idea la pueden hablar conmigo, la llevamos a un documento de unas especificaciones, unos términos de referencia y ya lo discutimos en un comité técnico que poseemos y vamos interactuando con los entregables, con la logística de desarrollo y siempre traen unos beneficios incalculables y una colaboración imprevisible, ¿cierto? Uno se encuentra sorpresas en estos trabajos muy gratificantes, ¿cierto? Información que uno no tenía a la mano o muchas veces uno maneja conceptos que son casi que unos mitos, pero hay una persona que nos puede proveer con esta solución. Bueno, entonces agradecer la asistencia a todos, a SIGRE Colombia por organizar estos eventos, al apoyo de nuestras instituciones, a ISA, a UPB, a XM, a GES, a MBM y otras empresas, así como a Transgrid, a Red Eléctrica, Siemens, Hitachi, entre otras que participaron acá, a Lady, Carlos, Vanegas, Eduardo, a los amigos y pues a muchas otras personas que hacen posible estos eventos. Entonces un feliz resto de día y los esperamos para la próxima. Muchas gracias.
Gracias.
Muchas gracias a todos.
Muchas gracias a todos
Excelente.
también. Y esperamos el próximo evento tenerlos también con nosotros.
Perfecto, muchas gracias. Y ustedes son como el motivo del esfuerzo de todos y resaltar a Jorge y a Henry y a todo el equipo de la Bolivariana y del SIGRE para lograrlo. Muchas gracias.
Gracias, Mauricio.
Muchas gracias a
Henry.
todos. Hasta luego.
Luego.
Muchas gracias.
También
Chao.
a Gabriel, a Mario, a todos.
Claro,
A
gracias.
los chicos, Manuela, David, Alejandro, Lady, todos.